Where we left off yesterday. Ready, set, go.
Okay, I'm gonna talk about two things. First, starting from the results that I showed you yesterday, I want to just go through how I like to visualize things, trying to having access to all the levels of the analysis that I'm interested in at the same time online. Meaning, I want to see the results of the segmentation. I want to see some maps, and I want to see some profiles across cortical depth, for example. And I want to be able to move between this, at least 3 different types of data at the same time. And I do this with AFNI and SUMA. I don't use them in a standard way, but it's a very flexible platform. So I bend it the way I want it. So this is what I mean. Here we can see live. There's not that much of an acceleration, but if you have a nice GPU, you can accelerate it and you can move it very, very quickly. Here you can see live that there is the surface reconstruction inflated of the left hemisphere. Here is left and right are inverted, or the left hemisphere of this participant. And the first color map here represents the intensity value of the voxel closest to the node in the surface, and it's just taken and copied. So basically, it's nearest neighbor interpolation. So we take the value of the gray matter, and then we plot it on top of the surface. And here, what you see, this is interesting for 2 reasons. This is interesting because we can see some structure. So you can see really high values around the central sulcus here, and we can see really high values around the occipital. So around here, this is reddish kind of thingy. And this is this reflects myelination essentially. So the sensory areas are heavily myelinated, and this is well known since post-mortem studies essentially. And that sensory area are really myelinated, and it's possible to obtain these maps confirming that type of finding based on a single scan. This is from Glasgow, an MP2 range scan. Another thing that you can see by doing this is you see this stripy patterns, this line pattern. This is basically leaking of curvature information into the anatomical contrast. And part of it has to do with errors in the segmentation, but part of it is biological, meaning that the bottom of the sulci is more myelinated than the top of the sulci. And so this is reflected in the surface representation. This is taken at 0.65 millimeter isotropic. So this is the resolution of the data. I'm gonna show you the same thing from some data that I acquired in Utrecht at 0.5 millimeter isotropic. And I'm gonna show you the difference because it's gonna look much more smoother. So meaning that there's gonna be less error in the segmentation just because the quality of the image is better. Because instead of taking 1 MP2 range as here as a standard in order to derive a good segmentation, we take 5.
Sorry, just to remind, so what you're protecting here is just the gray matter values?
Just the gray matter values.
You're just protecting to the surface?
Yes.
So
And
gray matter values from MP2 range, what do you compute?
From the MP2 range, I just take the, so here are,
compute a T1 like a synthetic.
is just the value of the MP2 range. Yeah. No, it's not from the T1 map. No. So here, the way the program is structured is that I, just for simplicity, I derive 3 surfaces. One close to the white matter. This is unsmoothed. One close to one in the middle, and one close to the pile, and then I smooth them. And in this case, I projected only from the one in the middle. Why do I project it from one in the middle? Because it's one that is the least affected by partial voluming in theory. Okay, this is it for MP2 range. And this is the result from the vanilla segmentation that I showed you yesterday. So there is no touch-ups or anything. And this is also a good starting point, a qualitative assessment of the segmentation. So if you see this pattern where you see like high contrast when you project the values of the anatomies, and you see high contrast at the level of the central sulcus and the occipital pole, that's a good sign. So because this is what you would expect. If you don't, there are two options. Either the segmentation is wrong, or there is some inhomogeneity in the acquisition. And I saw that many, many times. So this not only is interesting from a neuroscientific point of view, but it also is a good probe to check whether the segmentation worked properly, or if the acquisition doesn't, the acquisition have some inhomogeneities within itself that are not clearly noticeable just by looking at the anatomy.
What's the difference between generic research or segmentation?
This is, well, that's the thing. So I make it work on sub-millimeter data out of the box, and I never managed to make it work properly from free surfer with the MP2 range. Then the next thing is that, again, here we see the anatomy, we see the surface, and then we can say new underlay. Somewhere here we have the profiles. This is the profile of activity T1 weighted, T1 from white matter to gray matter. And this is something that I really like. So essentially, we can move anywhere in the surface, and it's going to show us the profile of T1 activity in this T1 signal in this case, from the white matter to the gray matter surface. And so you have an idea, and you can explore the shape and the size and the value of these profiles. Here I'm doing this just with a T1 activity, T1 signal, but if you have a co-register volume on top of it, you can do it at a single profile level with the T statistic of your model, or the coefficient, the beta coefficient, or whatever parameter you have. And I think it's a nice, it's a nice feature to have, because it allows you to explore the data not only from an average perspective, but online at the single profile level, and then you see all the nuances of the data. Now I'm going to show you the same thing from Xiao. I'm going to show you the same thing from a higher resolution version. This one, yes. Yeah. I have to open it in a slightly different version, different way, because it's quicker. Surfaces folder left, spec SV, around. I'm just going to open the surfaces because this is generated at 0.5 millimeter isotropic, and there are many, many, many nodes. So it's a little bit heavy on the server. So I'm not going to link it to the anatomy, but the principle is the same. And what I want to show you is the same thing, but just here there's going to be, here is high resolution, and there's going to be, at least to my eyes, there's going to be less of a leakage of curvature information into the map. Here we have the whole brain. This is not MP2 range, this is MP range, T1 weighted. Same thing, we have the surface from the middle. Then I remove the curvature information because we don't really care about that. Load, I already interpolated, copied the values on top of it. Loading them up. This is just the number of the node. Doesn't really care. We care about the aesthetics a little bit, so I put some shading there. And let me scale the values between something and something. That is good. And so here, compared to the one that I showed you before, this is the same thing. So we copied the value of the anatomy, of the T1 anatomy on top of the surface. And then you see the same pattern. Then you see the central sulcus lights up, heavily myelinated. And then you see some other things. The definition in the occipital lobe is much, at least to my eye, is much better than before. And the curvature, there is less of a curvature leakage here. So there is less of a stripy pattern that we showed before. This is because here the data is generated from a 0.5 millimeter isotropic acquisition, and we have multiple anatomies averaged together, and so you get a better result out, a better result that is more smoothed. And also the segmentation benefits from it, because we have this location here. This is around the ischial gyri, which is primary sensory area as well. And theoretically, it should be heavily myelinated. And this is what we see here, essentially. That we see this blobby here. This is corresponding to the ischial gyri. And whereas before we couldn't see it, probably because only from one anatomy is hard to get to this level of detail. I think this is an average of 5, so it's more likely to have this type of anatomical detail. Then what I want. Any questions about this? Good. Yeah.
So you scan this data only 70.
Yes.
Do you generally accept the quality of the temporal base?
Well, this was acquired at the Philips scanner, and Natalia knows more about that. But if the readout scheme in Philips in the Philips scanner allow us to acquire one anatomy at 0.5 millimeters isotropic with the weighting that we wanted in around 7.5 minutes. And so that allows us to acquire like multiple anatomies in one session, essentially. Whereas with the MP2 RAGE, you are forced to work with a scan of like around 11 minutes. And so it makes it harder to average like 5 or 6 at the same time.
I mean the temporal base.
No, the temporal
base. Yeah. So they have some degrading because the teeth stuff.
Yes. No. The temporal lobe are always a problem. Yes. I think Jaco optimized the sequence a little bit better for the temporal. At least I saw some images. And I'm going to show you another example with some functional data. And then I was surprised at the end. So this morning, earlier today, like we acquired an MP2 RAGE from here. And so I converted it, I ran it through the pipeline. I want to see how it looks. Believe me, I never looked at it. So maybe it looks very bad. Maybe it looks very well, very good. I don't know, but but first I want to show you some functional very quickly. So this was some functional data. Let me see. This is a small field of view. Same logic. So we open the surfaces, we open the anatomy, we can link the two, and there is this nice perk, a nice feature that we see the boundaries, so we know exactly. We have a nice visual assessment of the goodness of the segmentation. And here we can, there we go. Where am I? this is the surface generated and inflated from the Y matter border, approximately in the middle, and from the CSF. Let's stay approximately in the middle. And what you can do in this case, you can just let's add some stats here. Yes, we can project the stats on top of the volume. And we take these ones, okay.
This is the surface was extracted from a whole grain acquisition or from a partial?
This is from a partial volume. These were several acquisitions averaged together. And this from a partial volume T1 weighted time. And the results of the segmentation, this is heavily manually edited, but if you run this through 3D seg from AFNI, it's going to give a very good result. I have a little pipeline from that deals with partial volumes as well. Yeah, it's from a partial volume. This is manually edited, but I built a pipeline that deals with it also automatically. So from 3D seg and then with IRAS. And of course it works nicely, but the starting contrast needs to be good. And if you have a starting contrast like this, if you have a beautiful contrast, then really you can basically, well, not completely avoid the manual correction, but you limit it a lot. So that's, yeah, and the nice thing here, yeah, here again, it's just to show the flexibility, right, between surface activity and then some of the profiles that I'm going to show you. Here we go, and then we go back to functional AFNI. And let me range it to something realistic, 15. This is the beta coefficient. Clusterize it a little bit. Okay, there we go. And then let me move this one here. And let's say that we check the profiles of the anatomy because we like it. I like the anatomy, so I check the profiles of the anatomy. Anatomy. Graph. Right. So here we have three. There we go. And here you can see basically here there are the profiles of the anatomy. So the T1 signal from the gray matter, from the Y matter border to the CSF. Here there is the activity of a task, the contralateral visual activation, and here is the T-stat associated with it. And so we can see, like, if you go in locations that are in the middle of the cortical depth, there. Okay, this was lucky, fair enough. I didn't plan it. I kind of planned it, but not so nicely. Anyway, this is beautiful. So you see that in the middle of the cortical depth, there is this nice discontinuity. This is the stereogenic, basically. And probably if I drop the, here is smack on top. Let me try to make it bigger so you can see my point. So this is volumetrically built. So this blue line, can you see this blue line in the middle of the cortical depth? There is a blue line here. And this follows a volumetrically cortical depth, so is theoretically where layer 4 should be. But it kind of masks the underlying stereogenitality because it's smack on top of it. So I'm going to remove it. And if I remove it, we should be able to see it. I had to remember how to remove it. Control surface. I remove it everywhere. So you see that there is a whitening, whiter bit here in the middle of the cortical depth compared to the other locations. This is what we see at the profile level here. I hope everybody can see this. If not, tell me that I'm going. Yes?
Yes, and the recording is working. So you can zoom
Oh.
in on it later if you want.
Good. And then you let me see if I can move somewhere else. Yeah. Here. This is also really nice, really clear. There is this white band running around the middle of the cortical depth, and then you have this nice bump in the middle. Another thing that always with the profiling that I wanted to show you, email, sorry. Another thing that I wanted to show you just for the flexibility is that instead of overlaying the anatomy, the statistic, we just, I derived the profile of activity of the contralateral task, right? So you can do pretty much the same thing on the surface and at the profile level. Let me see if I can make it happen. So here I plot thresholding. Let's put thresholding. Let's not threshold anything. Okay, and then we make it like 2% or 3%, whatever. Here I'm projecting the beta coefficient, okay, of the activation associated to the contralateral task. So it's contralateral task. So in this hemisphere, there is little to none. There is some negative bold, but with this scaling, we don't see it that much. Well, we see it, but not that much. And this is the bulk of our activity here, right? And if we move, this is cortical depth, essentially. So this is very close to the white matter border. Let me scale it a little bit more. So there we go. This is very close to the white matter border. Then we can go more approximate around the middle. And then we see that there is this spread of the activity is a little bit more spread around the surface. And then towards the pile, even more it gets higher, right? And then, so this is on the surface level. Then you can see the same thing at the single profile level, profile left. The same way I derived the profiles yesterday that I show you. Then we can go somewhere in the middle. Yeah, where there is actually activity. Then you see that you move across the profile, and there is the classical, the typical profile of bold that from the white matter border to the CSF, there is the steep increase that also ran to show before for bold, right? So you have these three interdependent and linked way to show the data across the surface, on top of the volume, and across cortical depth, all at the same time, flexibly. So this is what I want when I assess and I check what the results of an experiment, right? Any questions? Cool. Okay, so shall we have a look at the MP2 rays that we acquired today? It's going to be less than 5 minutes because if it works, we see it. If it didn't work. And no, this one it was another acquisition that we acquired the data in Utrecht a few years ago. No, this is MP-Rage. MP-Rage.
I assume if people use like this for the match,
yes, as long as you have a good segmentation to start with, the method works for really. It doesn't care about the beginning contrast. As long as there is enough contrast between gray matter and white matter, it should work. That's the challenge. Really. Now let's see the results. Dunque, anatomy, I put them. Where am I here? No. Glasgow. Test CMRR. So now I'm nervous a little bit, but it's right. I mean, it's fine. What do I have to lose? Nothing. Like credibility. No, I don't know. Okay, the starting points are these two. So we have the obliquity is always an issue, but it's okay, it doesn't matter. The starting points are these two. So this is the MP2 raised contrast, and this is the second inversion. Oh, this is the second inversion. All right, we all see it, yeah. Then we take the anat copy. Okay, there is the file is already a good sign. That's all right. Okay. And then generally to just check the good, well, check whether something went right or wrong, I superimpose the cortical depth metric, and it's called something volumetric. There we go. Depth. And now see. Okay. Okay. It doesn't look bad. Let me close this thing. Some left over from the cerebellum. They didn't remove completely. But let me remove a little bit of the. Okay.
Looks awesome.
What did you say?
Is that like caudate nucleus getting
Oh, probably. Probably there were some issues here. Yes, yes, yes. But okay, this is not okay. Let's try to see what I said before. Right? This is not bad. Do we like this?
Yes.
Now, let's try to see what I said before, right? Afni surface. Now let me interpolate it. Just copy the values. Just because it's quicker. Do I have the time? How much time do I have? 3 minutes? 1 minute?
That's my grade. You can take off.
The inputs here. What is it? Surface folder. Of course. Let's see if this one. No, I did it already. Did I do it already? No, I didn't create the surfaces. Oh, no, too bad. Okay, I should have. Okay. Sorry, I cannot show the data on the surface, but at least we can see, yeah, it's going to take 10 minutes to create the surfaces, so I cannot do that. But at least we have the proof that the segmentation worked. The segmentation worked nicely with the associated profiles. So I'm going to just open those, and then I'm going to wrap it up. Profiles. Let's see how the profiles look like. These are black, of course, because I'm not in the cortex. And this is hard to assess, but at least we have some profiles that kind of, let's see if we go around the middle of it. Okay. We have some profiles, okay. They follow the trend. They should. From 1 MP to 8. You're asking too much. No, it's okay. They're nice and smooth. Right? Yeah, okay. So I'm not, yeah, no, I'm happy with the results. Okay. This is all I wanted to show you guys. Thanks a lot for your attention. Thanks a lot for giving me the possibility to finish.
All right, and I really don't have that much other content that I want to do. I would like us to keep having conversations.